Hey there, this is Mr. Alexander, and today what I want to do is talk to you about using RStudio to run the Anova analysis of variance hypothesis test. Anova is useful when you have groups that you want to see if the groups are the same or different. And the question I'm going to try and answer today is, do small dogs get adopted from the animal shelter faster than larger dogs? And the data set I'm going to use to answer this question is called the animal data set, and it's got a lot of different variables in here. It's got what kind of dog is at the animal shelter, what kind of animals at the animal shelter. It tells me a lot of things like the age. It shows me the color of the dogs and the cats. It shows me the weight. There's all kinds of good stuff in there. The thing that I'm interested in today is the animal type, which is dog, and the weight, because it says the data set tells us the weight of the dogs as a number. What needs to be done before we can answer the question using Anova? Well, Anova is only really useful when you have different kinds of groups. If we just have weights, we've got all kinds of numbers. We've got like a dog that weighs 10 pounds, we've got a dog that weighs 40 pounds. We really need to find a way to group the data. And so that's what we need to do. We need to group the data by the weights of the dogs. And that's what this code's doing here. It's taking these weights and it's just kind of arbitrarily deciding what's a small dog, what's a large dog, what's an average dog. Anything less than or equal to 20 pounds is a small dog. Between 20 and 50 is an average sized dog, and a dog that weighs more than 50 pounds, we're going to call that a large dog. So I'm just going to run that code. And when I do that, I can see now that there's a new variable, this weight group variable. And it's going to either be small, average, or large. That's going to be my grouping factor. I'm going to compare these groups, and I'm going to see how long it takes for them to get adopted. So the null hypothesis here is that all the weight group means are equal. Which is true of every Anova test. The alternative is that at least one weight group mean is different from the others. So if I'm trying to answer the question, how many dogs were adopted? Well, I should probably make a subset of just those dogs. So what I'm going to do is I'm just going to pull out the dogs. I'm going to say, okay, I'm going to make a subset called dogs, and actually I want to know the adopted dogs. So let's go ahead and pull out all of the animal types that are equal to dog, and I want anything, the outcome type to be adoption. So I'm just subsetting out, one more try. I've subsetted out, and it looks like the number of adopted dogs is 123. I can see that right there, because when I subsetted here, I've just got all the dogs that were adopted. So I come over here, how many dogs were adopted? It looks like we've got 123. And now I want to know, what is the mean time for adoption for small, average, and large sized dogs? Well, the time it takes for these dogs to get adopted comes from the variable days.shelter. This shows me how long they were in the shelter before they got adopted. So, in order to figure out the means of all three of these different groups, what I want to do is I want to use the aggregate command. And what I'm trying to aggregate here is those days in the shelter as a function of, looking for my tilde, there it is, as a function of the weight group that they're in. Now I got to specify for this command which data frame it's coming from. It's coming from dogs, the one I just created, and I want to know the means. When I run this command, it's going to tell me, well, okay, small dogs were in the shelter for about 14.94 days, large dogs 32.65, and the average sized dogs are about 23. Before we do anything else, let's look at the original question. The original question is, do small dogs get adopted from the animal shelter faster than larger dogs? Well, just looking at these means, those small dogs are in there for just over 2 weeks, and those large dogs are in there for just about a month on average. So yeah, it looks like they're probably different. But statistically, are they different? That's what Anova's to figure out. That's what we use Anova for. So those mean times, and those are all in days. Calculate the standard deviations for the groups and create a box plot. Are the assumptions for the Anova test satisfied? I'm going to calculate the standard deviations, I'm just going to copy this aggregate command. And instead of doing the mean, I'm going to do the standard deviations. And what I'm looking for here is I'm looking at the smallest standard deviation. And then I'm looking at the biggest. The smallest standard deviation is 20.445. The largest is 38.64. What I want to see is that the biggest one is no more than twice the smallest one. So twice the smallest one is 40.89. So as long as I don't have any standard deviations bigger than 48.89, I'm feeling pretty good. So yeah, all right, equal variances seems fine there. But I'm also supposed to create a box plot. And you can do that by doing the box plot command. And this box plot, we'll want to say which data frame it's coming from, what the quantitative variable is, as a function of the grouping factor, which in this case is weight group. And I'm going to go ahead and make this box plot. And I'm going to make it big. What we're checking for here is normality. Now, none of these things are ever going to be perfectly normal. None of them are ever going to be perfectly symmetric. What I don't want to see is something that's strongly right skewed or left skewed. Now, these things, they don't look particularly symmetric, but I'm not seeing anything that's like really left skewed or right skewed about them. I would say that these are symmetric enough. And it's kind of just an eyeball test. There is this hypothesis test that to test this specifically. We're not going to worry about that now. For now, we're just going to say, yes, variances appear to be equal. We should really say equal enough. And normality is shown in the box plots. Okay. Well, now we're to the bread and butter. We're actually going to run the Anova test now. Because I want to know what's the F statistic, what's the degrees of freedom between, what's the degrees of freedom within. You can do that by using the Aov command. But to do it, we have to have a model. Because that's how RStudio is going to visualize Anova. So we're going to say, okay, this model, I'm going to use the Aov command for Anova. I'm going to say, what's my quantitative variable? Well, that's the days.shelter as a function of what grouping factor? Well, that'd be the weight group. So it's always the quantitative variable first and the grouping factor second. So I've created that model, but I can't see it. So I want it to be summarized. So I want a summary of this model. And now I've got everything I really need. I've got my F statistic is 3.256. My degrees of freedom between is 2, and my degrees of freedom within is 120. So I'm just going to take a screenshot of that, because that's the easiest thing for me to do. And you'll notice that this is significant. This p-value is less than 0.05, which means I'm going to reject the null hypothesis. This null hypothesis is rejected because the p-value is less than 0.05. That means at least one weight group is significantly different than another. Well, that's what I love about the Anova tests. You answer one question and it leads to another question. It's like, okay, at least one weight group's different, but which one? What we need to do is we need to run a post hoc analysis. This post hoc analysis is imperative to answer the question, which group is different? So, what I like to use is the Tukey honestly significant difference test. And the command for that's pretty easy. It's just Tukey HSD. And I'm just going to put my model in there. And it's going to do all these pairwise comparisons. There's only 3. There's large to average, small to average, small to large. And what I'm looking for are any adjusted p-values that are less than 0.05. Well, it looks like there's one. It's small to large. What this says is that on average, small dogs are in the shelter significantly fewer days than larger dogs. Could I say the same about small on average and large on average? No, those p-values are too high. I can't show any statistical difference between these groups. But I can say pretty definitively that those small and large groups, they're different. So to summarize, small dogs are in the shelter for significantly fewer days than larger dogs. And that's really the whole Anova test. That's all the code you really need, is these lines here. And sometimes you don't even need this last line of code. If we had run the f-test, if I had run the Anova test and I saw an f statistic that was above 0.05, so like if this was 0.42 instead of 0.042, that says that all the group means are equal, and I wouldn't have to do this post hoc analysis, because at that point I already know that none of them are statistically significantly different. I could run it and I would just show that all the pairwise comparisons were the same, but I wouldn't have to. Okay, well, thank you for watching. That's Anova on RStudio, and I hope you agree that the answer to today's question, do small dogs get adopted from the animal shelter faster than larger dogs, is a definitive yes. Thanks for watching. See you next time.